All right, so we're going to take a quick look at a video of solving some logarithmic equations. And these are going to go from fairly simple to a little bit more difficult to just slightly more challenging. We're not going to do really hard ones today. We're just going to do some easier ones. The last one, we'll take a look at some laws of logarithms as well. So the first one we'll take a look at today is solve log 3x equals 4. So solving this logarithmic equation is actually quite easy because it's essentially just rearranging into an exponential form. And this is the reason why I show this is because what we want to do is we often want to get to a point where we have just a logarithm isolated on one side and can convert forms. So here we'll convert and we'll have 3 as the base, 4 as the exponent, and x is the value. And so then we just have to evaluate 3 to the power 4, which is 81. And so that would be a very simple logarithmic equation, and you can do a quick check. What's the exponent required to change 3 to become 81? Well, that's 4. So that one's absolutely true. So we'll take a look at the next problem. So the next problem is going to be just slightly harder, not too much trickier. A little bit more going on, though, algebraically. And so we're tasked with solving this. So we have 2 times the logarithm base 2 of x minus 1 is equal to 8. Just like with exponential functions, our first step is going to be to isolate the logarithmic term, and then we're going to aim to convert. So we'll divide by 2 on both sides first. So we'll have logarithm base 2, x minus 1 is equal to 4. 8 divided by 2, 4. Now we're at that point where we can once again convert. And so we'll convert to exponential form. The base is 2, the exponent is 4, and the value is x minus 1. So 2 to the power 4 is 16, and 16 plus 1 is equal to x, because we'll just add the 1 to both sides. And so we end up with 17 is equal to x. And once again, you'll see that this is a little bit more difficult because there's some preliminary algebra to do, but really quite easy. Once we have the logarithmic term isolated, we can simply convert forms. But that's not the only type of problem. I'm going to try and reuse this paper with something else. Because occasionally what we'll notice, a little mood change with the lighting there. Bulb must have burnt out. Maybe that's a bad omen. Whee. Anyways, let's take a look at another problem. So we're going to solve this slightly more complicated logarithmic equation. It's log base 3x plus log base 3x plus 2 is equal to 1. Now, when you have multiple logarithms, if they're the same base, then that means it's time to go ahead and use your properties of logarithms. If they're different bases, then you'd have to use a change of base and hopefully be able to manipulate some other technique there. So here we have the same base. So because we're adding logs with the same base, we actually just multiply the values. And this is how we're going to create that situation of having a logarithmic term on one side and another term on the other so that we can then convert forms. So here we used the product and sum rule to get us there. So when you're adding logarithms with the same base, you multiply their values. So that's why we have x times x plus 2. Okay, perfect. So now we'll go ahead and we'll convert this to exponential form. So we'll have x times x plus 2, because that's the value, and that's equal to the base, which is 3, to the power, which is 1. So 3 to the power 1. And we'll go ahead and we'll solve this. I think it looks like it's going to be a quadratic. Didn't I say there's going to be lots of quadratics everywhere? We'll move the 3 over to the other side by subtracting to turn it into a quadratic. And we're super pleased because this quadratic is going to factor nicely for us. It's going to be x plus 3 and x minus 1. Fantastic. And this is pretty easy to pick out your roots from. This tells you that you have x equals negative 3 or x equals 1 as a solution. But one of these things is not like the other. One of these things just doesn't belong. And the reason why one of these roots isn't valid is because if we go back up to the original equation, remember that log 3, a graph of a logarithmic function, has a vertical asymptote at x equals 0. So whatever's in the argument needs to be greater than 0. So negative 3 as a value of x means logarithm 3 to the negative 3. What power do you apply to 3 to raise it to negative 3? Well, that's simply not valid. This is in fact an extraneous root. It was created when we used this product sum rule to put these two things together. Because when we put these two things together and we multiplied, we introduced a situation where you could have a negative value times a negative value making a positive value that made this valid. In fact, if you graph this left-hand side here, and if you graph this right here, you'll notice they're actually two different graphs. Now, you won't be able to do this by hand. Well, you'll be able to do the top one by hand. At least each part of the top one, you'll be able to do it by hand. But the bottom one, you'd probably want to jump on Desmos and graph it. What you'll notice for the top one when you do them together is you'll have kind of this weird thing where you'll have a logarithm kind of emanating one direction. And that logarithm is going to start at a vertical asymptote at x equals 0. It'll move off in that direction. But when you do this bottom one here, you'll have this interesting thing happen where you'll actually have a branch going the opposite direction here. So it'll look kind of like a rational function in a sense that it can kind of dip down toward an asymptote. And that's because when you multiply two negative values together, you create this image of a positive value. So this is a root that we call inadmissible. And you should always check your roots back in the original equation. Go all the way up to the top. So here we could have actually told ourselves, well, if anything is negative, then it's not going to be a solution. If you had -1, it would work in this one, but it wouldn't work in this one. So we only have one possible solution, and it's x equals 1. What power do you need to attach to 3 to raise it to 1? Well, that's 0. And what power do you need to attach 3 to raise it to 3? Well, that's 1. So that is the correct solution. So the only solution is x equals 1. And that's how you deal with inadmissible roots.